Okay, I have a fun but simple math effect that can be performed for a single individual, a small group of people, or even in front of a large audience of people. Now there you probably would need like a chalkboard or a whiteboard at the front of the auditorium because you're going to have to do some elementary long division. Okay, now even though I call this a simple math effect, it still carries quite a punch, as you'll see. Okay, it's very surprising, and for 99% of people out there, they won't have a clue as to what's going on. So how this performance works, I call it a game in which you can win up to $1,200 if you make good choices. Okay, so first, the player randomly chooses any 3-digit number. Okay, now I do have a die here, a 10-sided die. Unfortunately, it has multiples of 10, so we'll go ahead and just use the first digit, and we'll use it to generate our 3-digit number randomly. Okay, so we'll go ahead and flip it. Okay, 4. So the first digit for our 3-digit number will be a 4. Okay, what about the second digit? A 6. Here we go, use a 6. And the last digit, a 5. Okay. So that is our randomly chosen 3-digit number. So the second step in this game is, in order to prevent a player from cheating by using quick mental math, the player's 3-digit number will be written down twice to form a 6-digit number. Okay, so what that means is you just take the 3-digit number and you concatenate it or juxtapose it with itself. Write it right next to each other. So now we have a 6-digit number that we'll actually be working with, okay? And this really does prevent any arithmetic savants out there from like quickly being able to figure out the answer in their heads. Okay, the third step involves the player selecting either 7 or 13 as their, quote, lucky number. So let's say they choose 7, which is commonly thought of as a lucky number. Okay, and then fourth, there is a catch. And so you can allow the spectator to go back and change that choice of 7 if you'd like, but there is a catch. A player can potentially win twice as much money by choosing 13, despite the fact that many people believe it to be a very unlucky number. Okay, so we'll go ahead and just assume the spectator is going to stick with the 7, which is fine, or they're free to change it if they would like. The winnings of a player are calculated by multiplying $100 times their 6-digit number's remainder upon division by their chosen lucky number. Now, since 7 as a divisor has remainders of 0, 1, 2, 3, 4, 5, 6, a player can win up to $600. Whereas, because 13 as a divisor has remainders 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, a player can win up to $1,200. Okay, so let's go ahead and we'll go with the numbers selected here, and we'll calculate the winnings for that player. So what we need to do is a little bit of long division. We're going to divide 7 into this 6-digit number here. Okay, so if you remember how to do this, in fact, your 5th grader probably will be better at it than most adults, and better than me, almost certainly. Okay, well, 7 doesn't divide into 4, but it does divide into 46 with a remainder of 4. Okay, so we'd put a 6 up here. 6 times 7 is 42 with a remainder of 4. Okay, and then we bring down the next digit, so that would put a 5 right here. So 7 divides into 45, 6 times, with a remainder of 3 this time. So we put 6 here as well. So 6 times 7 is 42 with a remainder of 3. Okay, and then we bring down the next digit, which is a 4. Okay, now 7 divides into 34 4 times with a remainder of 6. So we put a 4 right here. 4 times 7 is 28 calculate the difference there is 6. Okay. And then the 6 up above comes all the way down. You get 6 right here. 7 does divide into, but with a remainder of 3. Okay. So here we would put 9, because 9 times 7 is 63. There we go. With a remainder of 3. Now, if we were to stop here, if this was like the final step in the division, the player would win $300, which isn't too bad. But they do have one more digit way up here. It's a 5. So we bring down the 5. Well, does 7 divide evenly into 35? Unfortunately, it does. 7 times 5 is 35. Oh boy. So that leaves a big old goose egg for the winnings for this player. They win $0. Oh boy. They really should have chosen 13 or a different 3-digit number. Okay, and then you can play this over with another player. Now, most likely, if this were actually performed and then you have another player go, almost certainly they're going to choose now 13 as their lucky number because they might assume that since people think 13 is unlucky, as the performer, you don't want them to choose it because it actually works. Well, as we'll show you right now, no matter what 3-digit number they choose, and regardless of whether they choose 7 or 13 as their lucky number, the player will never win any money. It will always come up with a 0 remainder at the very end. So let's take a look at the quote secret. Why is that true? At the beginning, I did not in any way say that this is a fair game. That is a winnable game. I didn't say anything like that. What you could do if you're in front of, well, you can do it in front of an individual or audience, is fan out 12 brand new $100 bills and tell them that depending on their choices, they may win all 12 $100 bills. So they may walk out with $1,200 in their pocket that they didn't have before. And I chose the word may intentionally because, as we'll see, they are guaranteed to not win a dime. Okay, so what is the secret? I mean, think about this. How is this even really possible? Because they're given quite a bit of freedom here. They can choose any 3-digit number. There's a lot of them. So why is it that they can never win money at this game? Well, what we need to do is we need to look at essentially step 2. So step 2, so we have our 3-digit number. Let X represent the first digit, so it can be any whole number between 1 and 9. Y and Z can be any whole number between 0 and 9. Okay? So we'll just kind of leave them as variables. And so what we'll show you here will be a general proof, actually, for this result. Okay, so we take their 3-digit number, we concatenate it with itself, and now we have a bona fide 6-digit number. Now, I have a claim right here that we're going to verify in just a second, but this 6-digit number here is actually equal to 1001 times the original 3-digit number. Now, you might be able to see that in your mind's eye because of the simplicity of this number, 1001. But we'll go ahead and perform the multiplication in a second. So take that as a given for now, and we'll demonstrate it shortly. But if this is true, it really unlocks the secret that keeps the player from making a single dime, okay? Because 1001 has a prime factorization of 7 times 11 times 13. And now I did choose to just use 7 and 13 in this performance. Technically, you could also offer 11 if you wanted to, but I don't think that really strengthens anything. And it's kind of nice to have this narrative of a lucky number, which many people believe 7 to be a lucky number, and also many people believe 13 to be an unlucky number. So it's almost like there's a tension between those two. Okay, and the spectator's trying to figure out, okay, is the performer trying to use reverse psychology on me or something? Well, you're not, because it won't matter which one they choose. because 1001 has divisors of 7 and 13 for this game, this 6-digit number will also have divisors of 7 and 13, which simply means that when this number is divided by 7 or 13, it will always lead to a remainder of 0 at the very end. And that's the amount of money they will win. Okay. So let's go ahead and just kind of quickly confirm the rather elementary multiplication here, right? So 1001 times XYZ, okay? So of course Z times 1 is Z. Z times these two zeros, you get a 0, 0, and then Z times the 1 in the thousandth place gives you a Z. Now for Y, everything just shifts over, so you get Y, 0, 0, Y. For X, you shift over one more, you get X, 0, 0, X. And so if you just add the values in the corresponding places for this 6-digit number, you get Z, Y, X, Z, Y, X. So that shows that in fact, this number here is equal to 1001 times XYZ. Okay, so anyway, that's the secret to it. And you might want to think about, are there other variations on this that you can come up with that would be fun to present with maybe slightly different narratives that you generate on your own? So anyway, I thought I would share this on my channel. Of course, I'll put it in the Simple Math Magic playlist, which is where it belongs. A fifth grader could perform all of the calculations. Okay, so this is not a sophisticated problem, but what I like about this math effect is I believe the mathematics is very well hidden. It's not apparent to most anyone out there that this process is going to give rise to a multiple of the first 3-digit number, and the multiple will have as divisors two of the options that are being given for divisors. Right? So I think the mathematics is well hidden here, unlike a lot of math effects. Many math effects a mathematician can immediately see through. This one, they would have to give it a few moments of reflection and maybe even scribble some things down on a piece of paper to kind of work out, oh, okay, I can see what's going on here. So anyway, I thought I'd share this with you and encourage you to try it out on a family member or at a family reunion. That would be a fun place to do it. And of course, if you perform this more than twice, people will probably pick up on the fact that, wait a second, this isn't a fair game. You can never win. But if you were to do it twice, I think people would still be left with, oh boy, I should have chosen a different 3-digit number. Or I should have chosen 7 instead of 13 as my lucky number. Okay. So anyway, thank you for watching, and take a look at other videos on the Absolute Math Magic channel.